Okay, welcome everyone. Today, it's a pleasure to have Mukund Rangamani from UC Davis and QMAP, who is going to tell us about real-time gravitational replicas. So Mukund, please, the floor is yours.
Thanks. Thanks, Ignacio, and thanks, Mikhail, for the invitation. So indeed, I'll talk today about some work I've been doing in the last year on trying to understand real-time physics in the context of gravity. I'll primarily focus on applications to replica computations, but I'll just flash at the beginning a set of themes I've been exploring just to set the stage of what I am trying to do and what this broad goal is about. So today I'll primarily talk about the first two papers, the first of which appeared a few months ago with my student Sean Colin Ellerin, Ji Dong and Don Merolf, my friends from Santa Barbara, and Don's student Zhengcheng Wang. And the second paper upcoming sometime, hopefully soon. And both of these papers have been trying to set up, at least from a semi-classical gravitational path integral point of view, how does one set up and find stationary points for the real-time gravitational path integral? And how do we then understand, using that formalism, the dynamical evolution of various interesting quantities in the context of semi-classical gravity? There's a separate program, which I won't talk about, but if people are interested, I'll say a few words at the end, which has been to take a particular example of these kind of replica geometries, in fact, just what I would call one replica geometry, and use it to compute real-time correlation functions in ADS-CFT and study effective field theories of various kinds that various other people like Mikhail have, for example, studied in the past. Okay, so let me start with the goal and let me explain what the motivation is for this exploration. So at a single phrase level, the point is really understanding how to do real-time path integrals in the context of gravity, and learn how to sensibly study stationary phase approximation for such functional integrals. If you assume that semi-classical physics is relevant and we want leading G-Newton effects, then you want to understand what are stationary phases of the real-time path integral. This question clearly has a relevance to a wide set of questions, wide set of issues. And in the context of gravity in particular, it's become more and more important in the context of understanding the black hole information problem using islands and replica wormholes, et cetera, et cetera. But let's step back a second and just say that this question is poorly understood even in quantum field theory. It's sort of reasonably well understood in quantum mechanics, but it's not a question that's been really well studied and well explored sufficiently in quantum mechanics. And to say that, let me say that, for example, in quantum field theory over the last 15 years or so, we've learned to compute things like Renyi entropies, starting with seminal work of Cardi Calabresi and other people. We typically tend to do real-time correlation functions, but often all of these tend to work by using the Euclidean formalism as a crutch. You compute observables, assume that your observables have suitable analytic properties that allows you to continue those guys into the physical real-time domain. This is true if your sources, for example, for correlators are analytic, so you can just analytically continue the correlators you've computed in Euclidean signature. But it's not necessarily the case that all such physics is captured by such analytic functionals. But nevertheless, this strategy is very broadly pragmatic, and in many cases, it just tends to give you the answer. So it's very useful to know what's going on without getting hung up in trying to set up formalisms to compute things where we don't have analytic control. And this is most striking, in my opinion, when you think about gravity, because the Euclidean quantum gravity path integral in the last 50 years has been incredibly successful in telling us lots of deep insights about what's happening. Whether these deep insights correspond to how the physics actually happens in real time is never been made clear, but nevertheless, the answers are there for us to explain. So going back to the mid-70s, the seminal work of Gibbons and Hawking in understanding how black hole thermodynamics comes about by thinking about the thermal boundary conditions for gravitational physics, then onwards to computing Euclidean observables like correlation functions and just setting up the GKPW dictionary in ADS-CFT, and to more recent work, which I alluded to, this question of replica wormholes and black hole information problem that various of these folks worked out in the last 2 years or so. What I want to leave you behind is that none of these statements or calculations actually tell you what the dynamics in the problem is doing. They tell you what the answers are in various time domains, and they say that there's some imaginary time configuration that dominates at different regimes of real time, but they don't tell you how the real time evolution actually proceeds if you are trying to sort of watch the state evolve in real time. And therein lies the question, and that question is of course striking in the context of the black hole information problem, because while we might partially declare success and say the replica wormholes tell us how the page curve is obtained, they don't tell us what is the dynamical mechanism by which information is extracted out. So they just tell us the answer that the entropy, the state is pure, the entropy sort of works out correctly. And to sort of explain what the issues are, let me go back a second. Sorry, this is not how I wanted to do it. Okay. Right. To say what's going on, let's go back a second and just think about what is the real issue in trying to set up path integrals in quantum field theory or quantum mechanics even. And the real issue is one of causality. That if you're trying to do real-time physics, you need, and you're trying to compute something now, you certainly should not know something of what happens tomorrow. That causality constraint needs to be built into the real-time path integral. There's no such issue in the Euclidean calculation. So if you want to do a path integral or for example, say compute a density operator, you're given some initial state in quantum mechanical system, say rho naught, and you want to compute what happens to this rho naught at some later time. You want to compute its matrix elements. Then since this is a density operator, it has both a ket and a bra piece. The ket piece, as always, evolves forward with a unitary. The bra piece evolves backwards. And so you need to keep track of two different tracks of evolution. One, which is the evolution of the ket. The other is the evolution of the bra by the Hermitian conjugate. But if I'm interested in what's happening at this time, t, at some time t, which is to the future of t naught, I should also predicate my calculation by feigning complete ignorance of all evolution future of time t. I cannot assume anything to the future of time t, and that requires me to sort of absolve myself of knowing what's happening to the past this time. And so let me upgrade this picture in the context of quantum field theory to allow myself to draw both temporal and spatial information. So in this picture, the way I wanted to think about it is that I have some initial time slice at t naught, and there are two copies of it because I'm preparing some state in perhaps a mixed state. It could be a pure state, but either way, I'm preparing this state either by pulling it out of a hat or by preparing it by some Euclidean path integral and cutting it open to expose two different time slices. One piece evolves forward as the bra, as a ket. The other piece evolves backwards as the bra. And at some future time, I get to glue these things together to compute what's happening at that future time. So the future Cauchy slice is up here, and I'm interested in physics on this slice. I'm not interested in physics, what happens to the future. Now, this is not the issue. This is not the case in many calculations in high energy, which focus on scattering, and scattering is a conditioned observable where you start with some initial conditions and you know what the final state is. So you project on some definite final state. Here, I'm not assuming anything. I know what happens to the evolution, because in scattering, you assume that you sort of evolve forever, and then you project onto a particular set of final states. So So this would construct for me some object that's or some state at this Cauchy slice. And if I want to do something more, I could do something more. I could cut open this global state on this Cauchy slice and define partial reduced density matrices on subregions of that Cauchy slice. Okay? So all I need to do is when I, in my evolution forwards and backwards, at my Cauchy slice sigma, I demarcate some subregion of it and call it A, some other, the complementary region I call A complement, and they are separated by a separatrix, which is the entangling surface. And to compute density matrices on A, I just cut open the Cauchy slice in the bra and Ket pieces and prescribe initial conditions and final conditions and extract from this path integral with those boundary conditions specified on A, the two cuts of A, the, the corresponding density matrix elements of the reduced density matrix associated with it. So in this picture, I want you to imagine computing the path integral over all fields which are anchored in A complement, but leaving behind some specific boundary conditions for computing matrix elements on A. Once we have this, we can compute any set of observables. If you want to compute correlation functions, you can insert correlation operators at various places and compute them. You can also compute objects that don't exist in a single theory, but exist in tensor product of theories like swap Renyi entropies. And those would compute by, we would compute them by doing the replica trick. So we would sort of string together many copies. So to compute the replica entropies, you would string together many copies of this with some gluing conditions. I won't draw those gluing conditions just yet. I'll draw them when I draw them in the context of gravity. Let me pause here for a second to make sure that we're on the same page and the issue of what is to be done in doing real-time computations in quantum field theory is clear before I step over and upgrade this to the discussion in the context of gravity. Okay, so now I'm just going to repeat that exercise by saying a few words about how to extend this construction in the context of gravity, and that will set up for me the problem of doing replica computations in gravity. But before I do that, let me say a few words about what has been done so far and who's done it, just to give you some anchor points of what has been in the literature. So famously, the first set of replica computations in gravity were done by Lefkowitz and Maldacena, who basically gave a very nice story of how to compute, extend the Gibbons-Hawking path integral construction to compute von Neumann entropies for general subregions, and in particular derive the Ryutaka-Nagi proposal. That was later extended by Faulkner, Lefkowitz, and Maldacena, who showed how to compute quantum corrections, and importantly extended by Gidoun to compute Renyi entropies in quantum gravity. The formalism was already in Lefkowitz, Maldacena. G made very clear how to do the Renyi entropy calculations. And then Dong and Lefkowitz gave arguments in favor of the quantum extremal surface of Engelhardt-Ward. But all of this, I emphasize, was done in the level of Euclidean quantum gravity because they were really, in some very important sense, generalizing the discussion of Gibbons-Hawking to finite domains in spacetime. There's also a large and storied history, and I don't have all the references here, of trying to do real-time calculations in quantum gravity. There's a much older set of papers dating back to Son and Starinets and Son and Herzog, who tried to give prescriptions for computing real-time correlation functions in ADS-CFT, primarily motivated by understanding computations of retarded Green's functions in hydrodynamic limit. But I think the most comprehensive discussion was later given by Skenderis and Van Rees about a decade or so ago, who tried to argue how to build up geometries which were relevant for the kind of Finger-Keldysh path integrals I showed you in a moment ago. I used that with G and Aitor in trying to derive the HRT prescription a few years ago. And I also recommend very highly this paper of Manolf and Maxfield from last year, who tried to argue this in trying to use this for various purposes in the context of replica wormholes. And what exactly is the main difference between gravity and quantum field theory? Well, we can talk about gravity in general, but for the sake of simplicity, let me focus on gravity in asymptotically ideal spacetime. So what I'm really going to try to do is give you a story that sort of starts with some boundary quantity that I understand as a quantum field theory computation, and ask how would I set up the analogous problem in the dual ADS gravitational theory. So I've drawn here a picture, and this picture is supposed to represent just the ket part of the geometry. I'll upgrade this in a second. And the picture is supposed to mean the following. So I have some initial time slice, which is my orange circle. On this time slice, I prepare some density operator, or rather in this case, just a wave functional because it's just a ket. And I prepare that ket I've chosen to prepare that ket by cutting open some Euclidean path integral. So that's what this bottom hemisphere is supposed to represent. I then evolve that ket forward by Hamiltonian evolution to a later time, where on the boundary I have a Cauchy slice, which I've picked, which has been split into an A and an A complement, and there is a entangling surface, which is in this case 2 dots partially. Okay, so this sounds good. This is exactly what we had on the boundary. So if I was just focusing on the boundary of the cylinder, nothing changed from my previous picture. I just compactified my sheet into a cylinder. However, the prescription of a boundary Cauchy slice in gravitational theories, especially when the boundary is time-like, doesn't uniquely specify a bulk Cauchy slice. There's a whole codimension 0 volumes worth of regions that the bulk Cauchy slice can pass through. And I've drawn a particular representative that sort of straddles somewhere in the bulk. All this Cauchy slice needs to do is be everywhere space-like from from the boundary Cauchy slice. Every point on this bulk Cauchy slice has to be space-like, separated from the boundary Cauchy slice. So that's a choice I've made. And I've also a priori chosen to break up this bulk Cauchy slice into 2 regions, which I'm calling RA and RA complement. I'll call these the homology regions because they will be homologous to A and A complement. And they in turn are separated by a separatrix, which I'm calling gamma here, this red curve. Gamma is codimension 2. It is the proxy for the RT or HRT surface. In fact, it's going to be slightly more complicated than that in the language of G like to use for its Rayleigh entropies. This will be the cosmic brane. But now that was just the construction of the ket. Now, if you think of construction of the density operator, the density operator would require me to have one such copy for the ket, another such copy for the bra, with appropriate time flow forward in the ket and backward in the bra, and cutting open not just the boundary, but also the bulk Cauchy slice along the separatrix and gluing the homology surfaces associated with a complement to each other between the bra and the ket, leaving behind boundary conditions to impose here and here. And that should compute for you the gravitational density matrix, at least in the semi-classical level, for the state on RA which is bounded on A. So it's exactly the picture from before. I just don't show the gluing explicitly, but just show the gluing as an identification because I don't know how to draw these gluings in higher dimensions. So that's the 0th order construction of the density operator. This is just with some boundary conditions, just prescribes rho of A in gravity. And now if you want to compute complicated things like Rayleigh entropies, you take this guy as your elementary Lego building block, and you put together many such copies, and then you have gluing conditions. What are the gluing conditions? In every bracket pair that makes up the density operator, the complements are glued to each other, but the ket of one replica is glued to the bra of the other replica, and the bra of the other replica is glued to the ket of the other or the first replica. So I've just drawn rho squared here. This is computing in some sense trace rho squared in gravity. And if we're computing rho cubed, then there will be a corresponding cyclic thing. Ket 1 goes to bra 2, ket 2 goes to bra 3, and then bra 1 goes to ket 3. And that's the cyclic gluing of various bras and kets, respecting the cyclic replica symmetry. So before I proceed, I want to define various domains in this geometry, some which are drawn and some which I'm going to just indicate by hand because it's trickier to draw. So let's see. So we had our boundary Cauchy slice, which was split into A and A complement. There was a corresponding bulk Cauchy slice sigma tilde, which is a choice right now. We have to choose, we have to decide where it is. We don't, as of now, we haven't decided where it is. We've just made a choice. We haven't actually solved an equation. So this is an ansatz, if you like. There's a homology region for A. There's a homology region for A complement. And there is a splitting surface, which is important because this splitting surface is common to all the replicas. It's common to the bras and kets. Yes?
Yeah, Mukund, just a quick question. So, like, wouldn't you say that the geometry is not going to be specified unless you glue these things together?
Correct. So yeah. Geometry is not specified. So this is indeed just an ansatz construction. You're quite right, Michal. And what I'm going to try to do once I've given you this ansatz is tell you what boundary conditions I need to use and what is the variational principle to solve for the equations.
Okay, good. Thanks.
Yeah, thanks. That is very important because right now we haven't solved any equations. In the field theory discussion, remember, just because the boundary is non-dynamical, there the cutting and gluing is something I can do for free. It's just that I have to solve the quantum fields on that cut and glue geometry. But here, Michal is rightly pointing out that I haven't done anything because these are just pictures at this point. I have to solve equations. So the thing that one domain I want to, one geometric quantity I wanted to pay attention to is the splitting surface gamma. It's codimension 2 in space-time, and it's common to every bra and ket, and it sort of is the point that's common to all the replicas, is a domain that's common to all the replicas. There's another geometric domain which I will use, which is this notion of the homology wedge. And let me define it as follows. Given RA on any given ket or bra, there's a past domain of dependence on the kets and future domain of dependence of this on the bra, which I'm going to call the homology wedge. It's a full codimension 0 volume. It's a set of all points that is in the bulk, which is space-like to A. And past of this Cauchy slice on the ket and future of this Cauchy slice on the bra. The future and past I'm just using going by the direction of the arrows of time. For those of you who are familiar with the notion of entanglement wedge, this is exactly like the entanglement wedge, except that's only one half of it, and it refers to each bra and ket component separately. I'm not going to call it the entanglement wedge because it's associated with this homology surface, and for exactly the reason Michal said, that I haven't solved equations and I have to figure out what's happening in different geometric domains. Perhaps the reason to isolate that statement is to make clear the following. In gravity, we have this codimension 2 surface, and there is this piece of the geometry which is space-like separated from this codimension 2 surface let's say in this particular ket in the past. But there's also a piece of geometry which is time-like separated, time-like past of this codimension 2 surface. And the characteristics of the geometry and what's happening in these 3 domains is going to be different, and we're going to treat them separately in what goes on. Okay. And this is related importantly to the notion of causality and what boundary conditions and how the variation problem is set up. Good. So now we can say, I can say what's going on. So let me now try to specify the problem in one slide of what we want to do. Given the replica construction on the boundary, i.e. given some initial boundary state and correspondingly some, if you know what the corresponding geometry is, the bulk geometry at early times, and a time at which I want to compute some Renyi entropy in the boundary, I construct the boundary replica manifold, which I call Bn, which is obtained by a boundary cut and paste construction where I just cut and paste on the boundary for free with boundary conditions for quantum fields on this Bn. Bn you can think of as an Enfold branched cover over the entangling surface. I then want to ask, what is the saddle point of the gravitational path integral, which computes for me the partition function of the boundary quantum field theory on the boundary manifold Bn. Standard story in ADS-CFT, you give me boundary conditions on the asymptotic time-like boundary. I try to find the bulk geometry, and then I try to construct for you do the path integral over the bulk fields and construct for you the boundary partition function. What is the bulk action? The bulk action I will write in importantly as e to the is, so it's really a real-time path integral. And S itself is composed of three pieces, one coming from the kets with a plus sign because kets evolve forward, one coming from the bra with a minus sign because of the Hermitian conjugate, and I'll separate out the contribution from the splitting surface, the codimension to splitting surface, okay? Because this is a locus where things are going to be funny. If I can compute Z of Bn some way, then the boundary Renyi entropies are obtained by basically the standard construction. I take the log of ZBn divided by the normalization factor for where B is the original boundary manifold, divided by this usual factor 1 minus n. And I can write the answer in terms of this, in terms of the action. So if there is a saddle point evaluation of Z of Bn, then I can write it in terms of the on-shell action of the bulk manifold Mn whose boundary is Bn. And the question amounts to asking, how do you find Mn given the boundary Bn? Let me make the claim for now and then justify this claim in the next set of slides. The claim is that this, okay, let's see one thing without doing a calculation and see where there's an important wrinkle in this calculation. When we do the Euclidean calculation, everything will be fine because first of all, there's no distinction between ket and bras. If you do the Lefkowitz-Maldacena calculation, there's just a Euclidean action. It's e to the minus s Euclidean. And you can separate out the bulk piece from the cosmic brain piece. And you can excise the cosmic brain and do the calculation with the cosmic brain excised, as Lefkowitz-Maldacena taught us to do. The good news is that all the Euclidean geometries that we speak are real Euclidean geometries. The Euclidean action is real. Therefore, there is no surprise that the Renyi entropies are real. Of course, Renyi entropies have to be real because they're entropies. In this calculation, I have a phase in the path integral measure. Actions are presumably real, but these are real functionals of metrics and fields in the bulk. And unless those metrics or fields in the bulk are complex, this phase is not going to get converted into a real answer for the Renyi entropies. Okay, so I'll convince you of two things. A, I'll convince you the metrics are complex, and B, the actions therefore do have an imaginary part. And the physical answer is basically given by the imaginary part of the on-shell action. And I've written it in a very particular way. I've written it for the on-shell action on the nth bulk geometry, but just focusing on the ket pieces. Okay, so this K refers to the fact that this factor of 2 is a statement that the contribution can only be thought of as coming just from the ket, and the bra basically adds up. So to give you some intuition before I even dive into the calculation, let me say it this way. The actions are going to be complex. The real part of the action is going to cancel between the kets and the bras because of the I and the relative sign. The imaginary part of the action is going to add between the kets and the bras and going to give you the physical answer. Okay. This is important, and we'll see how this comes about. Let me pause to ask if there are questions about the setup before I then show you how justify in words at least this claim. All right.
Sorry, like another question about the calculation. So, yeah, when you glue Euclidean and Lorentzian pieces of the boundary, like, is it clear that the metric that you obtain in the bulk, like, you know, that you would be able to glue these two things together in such a way that the metric is real and like it just changes the signature?
No. Okay. So let me clarify one thing, Michal, and then answer the question. In the boundary, I'm cutting and gluing real metrics. So in fact, let me make my life simple and assume that in the boundary, I never go do a Euclidean excursion. So that's why I do the sharp tens. So I come up to some Cauchy slice and just go down. There's no Euclidean excursion. We can do an I epsilon and do Euclidean excursions, but let me say I don't do that. So in the boundary, there's nothing imaginary yet. Your intuition is right. In the bulk, the metric is not going to be real. I just have to explain to you where it's not going to be real and why it's not going to be real. Okay, and that's where this imaginary part will come from, because the imaginary part can't come from the action evaluated on real metrics.
Very good, thanks.
Okay, so I'll split the problem into a couple of steps. I'll forget about the splitting surface for now and focus on the homology wedge. So let me see if this works. So let me focus on this domain that's space-like to A in the bulk. Okay. Well, I can do a variation of the gravitational action and write it in terms of the usual statement in terms of variation of metric and variation of extrinsic curvature. And I'll focus, see, first of all, let me say this. If I focus away from the splitting surface on the homology surface or anywhere in the homology wedge, then nothing really is happening, because this is almost like the problem where because of causality, geometry can't know what's to happen at the splitting surface because these regions are space-like from the splitting surface. So this part of the problem should be almost as if you can solve it without knowledge of what boundary conditions you need to put on the splitting surface. And in particular, if you look at the variations, you'll see that both the metric and the extrinsic curvature should be smooth for gluing across the homology wedges. So in this picture, this gluing is completely smooth. Metric and extrinsic curvature smoothly extend from this to this, and likewise from here to here. More importantly, if you assume replica and CPT symmetry here, I just mean a symmetry that exchanges bras with kets, then because of the way the gluing works, and you can sort of generalize some discrete symmetries, you can check that the metric must be real in the homology wedge. Okay. The reason, again, is just the fact that this is space-like separated from the entangling surface. Nothing can happen there. So we've answered half of Michal's question. The metric is real in the homology wedges of both A and A complement. We haven't said what's happening on the splitting surface, and we haven't said what's happening in the causal path of the splitting surface. Okay, and therein lies the problem. The problem is the following. If you think of what's happening on the splitting surface, we have a Ket light cone from one replica, which is pointing in some direction. We have a Bra light cone in the corresponding partner. And then we have such Bra Ket light cones for every replica copy. So we have 2n light cones. You have to have 2n light cones, which are all pointing in some direction of time, which are not the same because they're pointing in different domains. And you have to try to smoothly glue them together to make a Lorentz signature metric. Not possible. There's no real metric which is smooth and has more than such gluing of 2n light cones. Note, this is not a problem on the boundary, because on the boundary, I never needed smoothness on the entangling surface. I just cut and glue. Because gravity is not dynamical, I just cut and paste. In fact, we know what the answer is. If you're trying to build a Riemann surface in 2D, by gluing together the entangling surface is really a branch point, and it's a source of source of energy, so the space curves around and makes the appropriate Riemann surface. But gravity is special. Gravity, I have to solve the equations and find smooth metrics. Otherwise, I haven't solved a saddle point equation. Okay. So, and therein lies the catch. The catch is going to be that in the causal past/future in the Ket and Bra, respectively, of the entangling surface, I need complex metrics. I might have to have complex metrics. So let's zoom in on that and see what's happening. So now, this picture may help a little bit to clarify what I just said. So here was A. I've just taken a slice of my cylinder. This region here was the homology wedge of A. And there I just told you the problem is nice. There's nothing to do. Here is the homology wedge for A complement. Here also the things are nice. There's nothing to do. The problem is outcomes from the plane of the slide, the splitting surface, and this is the light cone coming off it. And down here is my question mark region where I have to understand both the variational principle and tell you whether the metric is real or complex. Let me, we can do this carefully, but let me, for the sake of simplicity for the second, imagine just taking a sort of vertical slice through this slide and drawing a two-dimensional cross section. So here is my homology surface for A. Here's my homology surface for A complement. Here is a splitting surface, and here is a light cone emanating from it locally, going back in the Ket. Let me regulate the homology surfaces by excising a tubular neighborhood of the splitting surface. So I take the splitting surface and just excise a little tube around it. I want to do exactly what Lefkois-Maldacena did, of basically removing this from my geometry and studying what happens as I approach this singular locus. Okay. If we pretend for a second that this is like a two-dimensional problem, then the action, the gravitational action localized to this splitting surface is basically up. And now I've put all the signs here and the eyes to correspond to Lorentz signature. This guy, whether it's, and the eta refers to Ket/Bra, this guy, the Einstein-Hilbert term, I can rewrite for a second in terms of the Gauss-Bonnet formula. Okay, in 2 dimensions, this will be an exact statement. I'm just going to sort of generalize that to higher dimensions. What is the formula saying? It says that the evaluation of the Einstein-Hilbert term is related to the evaluation of the extrinsic curvature on this cutoff, plus a term coming from the Euler character times the area of the surface. Now, in Euclidean signature, there would be no eyes, and this will be really the Gauss-Bonnet formula. The statement that I'm making is that there's a suitable generalization of the Gauss-Bonnet formula to complex matrix, which just puts the eyes in the right places for things to work. And this was not original to us. This was pointed out by Luca and Sorkin long time ago in the context of topology change in gravity. So we're going to use this formula, and I'll justify it later. But this formula will already tell us how to set up the variation problem. Okay. So key point, metric is real here and here, but not necessarily real here. And we'll just try to evaluate the contribution. So contributions from here will be nice, and we can evaluate them. The contribution from here, I'll evaluate separately. Good. So there's a nice trick to see how to evaluate these actions with the cutoffs and so on. And the various ways to do it, but here's one way to do it. So we have one parameter, which is the Renyi index, n. And all we really have to do is, given that Renyi index, we build the replica geometry. And we can think of the problem in two different ways. We can either think of the problem in the Enfold cover, or as Lefkowitz-Maldacena taught us, think of the problem slightly more in a slightly more compact form by taking the Zn quotient and working in one fundamental domain. That has the advantage that I can focus on a single ket geometry or a single bra geometry. And on a single ket or bra, I can say, okay, I have, instead of a splitting surface, a conical singularity of some strength. If I just take a Zn quotient, the strength of that conical singularity is set by n. Okay, the tension of the cosmic brane is set by n. It's 1 minus 1 over n. But that requires me to solve all of Einstein's equations at the same time, which we can do. But let me separate out the problem and introduce another dial. Let me introduce a canonical conjugate pair, one which is a new variable m and its canonical conjugate a, the area of the surface. In other words, let me imagine solving an auxiliary problem for a second, where I put a cosmic brane of any strength I want, specified by m, and still try to solve the problem for the nth Renyi entropy. Okay. This will be just a two-step process. We don't have to do this two-step process, but it's just easier for me to write equations and tell you what the boundary conditions are. So if you take the Zn quotient and work in a single copy of the ket, usually you would have said, I have a cosmic brane whose tension is 1 minus 1 over n. I'm just saying, call the tension m, and let n be a parameter that tells you that you have to wind around the cosmic brane n times to get a smooth geometry. Okay. Then I can split up the variational problem in a two-step way, where I first impose all the Einstein's equations while holding the area of the cosmic brane fixed, or effectively while holding the tension of the cosmic brane independent of the geometry I'm solving for. At the second step, I impose the equations of motion coming from demanding that the cosmic brane has the correct tension to be the nth Renyi geometry. Okay, so this strategy we used from a very nice paper by Ji and Don, who talked about fixed area surfaces along with Don Hallow before, and then in a second paper, Ji and Don used it to explain. They were motivated by trying to understand tensor network states as fixed area states in holography, and that's where this discussion came from. So if I define the piece of the gravitational action with the cosmic brane excised as S check, the two statements you can make. One is the variation of S check with respect to the arbitrary brane tension is proportional to the area, with now an extra I coming from the fact that you're in Lorentz signature. So this you can basically go back one step to my previous expression and see that it comes from the complex Gauss-Bonnet formula. More importantly, you can then look at the local geometry near the singular locus, and you can write down an ansatz in light cone coordinates. So this is exactly what was done, for example, in Lefkowitz-Maldacena or later by G, where they were trying to adapt Gaussian normal coordinates to the cosmic brane. Except that now the difference from their discussion is that, and we use that with G and Itor, but the distinction in the Lorentz signature is that the cosmic brane or the splitting surface is space-like, its normal plane is time-like. It, in fact, the Lorentz is a copy of Minkowski space in 2 dimensions. I'll parameterize that R11 in terms of light cone coordinates x plus and x minus. Strictly speaking, if you want full disclosure, these are not quite light cone coordinates. These are light cone coordinates adapted to the space-like domain. So this is the usual light cone coordinates of the sign flip. So these are positive in the space-like domain and negative in the time-like domain. And you have the sort of standard metric components in the, you have some fibration over the base. Y's are intrinsic coordinates to the splitting surface, and x plus and x minus are the normal plane coordinates. And smoothness of geometry upstairs tells you what tolerance you have on these metric functions sigma, t, w, and q's as functions of x plus x minus. The singular locus is at x plus x minus equals 0. These are the origin in this plane. There are many ways to get this. The easiest ways to get this is to go back to Lefkowitz-Maldacena or this Dong-Marov discussion and inherit what they did in the Euclidean computation back in Lorentz signature. Because that discussion is local, it doesn't care about signature, you can just impose it as a boundary condition, what happens. Then with this ansatz and this variation, this is the last Einstein equation I need to impose, okay? So this is the M is going to be arbitrary. As you can see, M is a parameter in this action, in addition to N, which is the Renyi index. I will impose stationarity or smoothness of this geometry, and then finally impose this equation. But before I do that, let me say a few words. I said earlier that the Lorentz signature metric can be smooth. In fact, it has a problem. What is the problem? The problem is you have a codimension 2 surface on which you're putting some source of energy density. You're putting a tension. Now, any energy density in Lorentz signature is going to disperse along caustics. Because the gravitational problem, if I put local energy on at a point in 2 dimensions, it's going to propagate along the light cone. In odd dimensions, it will propagate in the light cone, but definitely on the light cone, I have a cut. So if you're thinking of this in that language, then to go from the space-like region, which is the homology domain, homology region, the homology wedge, to the time-like domain, which in this picture is here, to go from here to here, you should really think of crossing a branch cut going down the light cone. Because there's a source of energy here, and that propagates down this. And that's like saying that, you have to analytically continue your data from this side to this side. But like with any dispersion calculation, that requires an I epsilon prescription to jump the cut, because there's an explicit discontinuity going across this light cone cut. This may be easier if I say the following set of words. Imagine computing a 2D conformal field theory 2-point function, x minus y to the 2 delta in Euclidean signature. If you analytically continue to Lorentz signature, so this is the correct answer in the space-like domain in Lorentz signature, because x and y are the only singularities are coincident singularities. But there is a light cone cut because now there's a branch cut of strength delta as you cross the light cone. So going from the space-like domain to the time-like domain requires an I epsilon prescription to get the correct Green's functions in Lorentz signature. And we can work out what that I epsilon prescription is, and that I epsilon prescription basically wants you to continue the plus and minus in this way. Once you have the I epsilon prescription, which I will explain in an example in a second, you can just compute the contribution from the splitting surface by using this Gauss-Bonnet formula. And you'll find that the contribution is basically given by m-1 times a gamma. So the total variation of the action with respect to the area is basically proportional to m-1. This was the last Einstein equation I needed to impose, because I was keeping the area fixed by keeping the tension decoupled from the Renyi index. When m goes to 1, the variation of the action with respect to m basically gives you the area over 4 g Newton. But importantly, it gives you area over 4 g Newton with an I. Therefore, e to the is does give you real area over 4 g Newton. Okay, so this is very abstract. So I'll do an example in a second. But before I do an example, let me give you a pictorial example by just talking about it, which is very helpful, which I found very helpful in understanding this problem. Let's try to do the Gibbons-Hawking calculation in our head. And remember that Gibbons-Hawking took gravity with a asymptotic time-like circle and said, let's find out all the geometries that contribute. And they said there's an important geometry, which is a cigar, which is topologically a disk, which is the Euclidean black hole. And then they computed the on-shell action by computing ρgr plus counter terms. Like in ADS-CFT, you'd have to add counter terms. In flat space, you don't have to add counter terms. It just gives you ρgr, gives you the answer with the boundary term, the appropriate Gibbons-Hawking boundary term. But let me pretend for a second that the geometry, this is the computation is involved because there's the geometry is not a cigar times a sphere, but it's really a cigar fibered over a sphere. Because R talks to both the sphere and the TR plane. But let me pretend the geometry is a cigar times a sphere. So sphere goes along for the right. So it's a transverse space. I get an area contribution by integrating ρgr. The cigar has the topology of a disk. So Euler character is 1. In fact, 4 pi. So I get 4 pi times Euler character times area divided by 16 pi g Newton, which is area over 4 g Newton. Okay, this is a very crude way of getting the answer because it's not exactly how the computation works, but this is spiritually correct. If you weak rotate Euclid to real time, there's an I in front of the action, but the complex Gauss-Bonnet formula gives you I area over 4 g Newton, which compensates for this I, and you get back exactly area over 4 g Newton. So again, this is not original to us. This was discussed by Yasha Niemann and also by Sorkin and friends a long time ago, but it's a very useful way to understand what's going on. Okay, so I assume I have another 5 minutes or so, Ignacio?
Yeah, sure, go ahead.
Okay, so let me, so that's the problem. That's the variational problem. That's what we discussed in the first paper. But it is indeed abstract, so and it sort of says what boundary conditions they want to impose. The problem is that we only solve the variational problem. As all of you can appreciate, actually solving geometries is trickier. But you can make progress, and the second paper, which should come out sometime soon, does make progress in low-dimensional gravities where the gravitational problem is tractable. Okay. So I'll give you one example here, and then I'll say one more example in words afterwards. And the first example I'll discuss is a computation in something that I don't think should be called gravity, but it is JT gravity in the thermophile double state. So here's the action, purely topological gravity theory with a dilaton. Okay. The standard JT gravity theory and there's a overall coupling set by the value of the dilaton. We can try to do the state I prepared. So this is the solutions here are just ADS2 with some dilaton profile. And I'll pick the state, which is the global ADS2, which I should think of as the thermophile double state between this boundary and this boundary. Now, what I want to do is I want to take n copies of this. I want to cut this thermophile double state into 2. I want to compute the entanglement of this half with this half. Or rather, I want to compute Renyi entropies of this half with this half. But in this case, the answer is simple because famously, the entropy is independent of temperature, and therefore the Rayleigh entropy is independent of Rayleigh index. Okay, the answer is very straightforward. It's just phi naught over 4g. Universally, it doesn't care about what the Rayleigh index is. So let's try to recover that. How would we recover that? First of all, we have to construct the Enfold replica gravitational geometry. But gravity is so simple here that the answers are all ADS2 in some funny coordinates. Okay, so this is ADS2 quotiented by n to construct for you the corresponding geometry for one domain, in this case, one ket of the Enfold replica. Okay, you have to glue n copies of this together to make exactly the geometry we're talking about. And here I will use some familiar language. I'll call these homology wedges the Rindler wedges, and this time-like domain the Milnor wedge, because it's exactly what it is for this one point in this. I have the geometry, and I'll call this prefactor function sigma for later reference. There's a dilaton, which is function of the light cone coordinates in this case, but it's boring, so we don't have to worry about it. It's not going to contribute to the entropy. So I'll just tell you without justification for now, believe me that this piece doesn't give you any contribution to the entropy. It's just everything comes from here. So we'll try to compute this. How are we going to compute this? We have the solution, we just have to compute the on-shell action. And I'll show you mechanically in the next slide how this on-shell action is computed by doing the following. I'm going to take this one copy of the ket, and I'm going to cut out the semicircle from it. And I'm going to compute the action using the complex Gauss-Bonnet theorem by using the Euler character of the plane with a disk cutout, half disk cutout, and computing the boundary terms on this surface. But before I do anything, just see one thing. X plus and X minus, I said, are positive in the space-like domain. So then one of them is this product is negative in the Milnor wedge. This is the cut I was alluding to, 1 minus n over n. So going from here to here, I pick up a phase. There's one easy way to say that we can assign, as you cross each light cone, you pick up a phase of I pi over 2. Okay. The light cones sort of tilt around. There's an easy way to say it. So if you look at the normals to this surface, to this cutoff surface delta u, then the normal here is pointing in the space-like direction. Normal down here is pointing in the time-like direction, which means somewhere here the normal is pointing in the null direction, which is terrible, but it's sort of tangent to the surface. So the normals switch signature from going from space-like to time-like, which means there's a pole in the inner product of the normal at exactly the light cone. Integrating over that pole gives you a factor of pi over 2 from the I epsilon prescription. Okay. So let's put some words, let's put some mechanics to it and see what happens. The on-shell action is just the gravitational part. I'm just dropping the dilaton. I'll write as 4 pi times the Euler character minus the Gibbons-Hawking term from the new boundary from the excision, plus some corner terms which may be present if my surface doesn't hit the cutoff, doesn't hit this time surface perpendicularly. Okay. There may be some additional terms lurking in this corner, as people have discussed in the context of various complexity calculations. So you can compute these two pieces independently. I'll just focus on the Gibbons-Hawking term, and both those pieces combine together to give you the correct answer. But let's compute the Gibbons-Hawking term. Pick any function of u x plus x minus to define this surface, and then just compute the extrinsic curvature. So as a function of this function u of x, say x plus is u of x minus, there's some piece which is an integral of derivatives of u. It's like some kind of Schwartzian kind of piece coming from this guy. And then there are derivatives of this scale factor with respect to x minus, and a corresponding piece with respect to x plus. This is just explicit evaluation of this term. Okay. The point is that this guy has cuts on the light cone because of the branch cut. And this integral, you just evaluate by using the principal value prescription. Because of my I epsilon said you go x minus goes to x minus plus I epsilon, and x plus goes to x plus minus I epsilon. So each of these integrals gives you an imaginary piece with an I pi, localized at the cosmic brane. And there's a real piece, which is just the principal value. But this is the contribution of the ket. There's a corresponding contribution from the bra. The real pieces cancel, the imaginary pieces add, and the action gets you what you want. So mechanically, it couldn't have been anything else. This is a Euclidean geometry. I could have just done the computation in Euclidean space with a thermofield double state, and I would have gotten this answer straightforwardly. Because then I would have just put a conical defect of size n. I would have gotten to covering space, which is radius 2. The action of radius 2 is whatever it was. I would have just gotten phi naught over 4g Newton. The difference is that the organization of the calculation is quite different in this case, because of the fact that the contributions are not localized here. They're coming from jumps across these guys. But effectively, because these are cut integrals, they're sort of effectively localized at the splitting surface. So this is one example that can be done explicitly. We have a couple more examples, mostly in 2D or ADS3. We managed to reproduce this very beautiful calculation of Tom Faulkner for Renyi entropies of disjoint intervals of arbitrary domains. Basically exploiting his strategy and suitably rewriting it in Lorentz signature. So that should hopefully come out sometime soon. So I think I'm just about out of time. So let me say that most of the talk I basically gave you the general variational principle for analyzing real-time replicas in gravity. We sort of focused on trying to compute Renyi entropies in simple setups and just setting up the problem. One can imagine doing lots of interesting things with it, of trying to compute loop effects, computing islands more carefully, etc., etc. We haven't done that. And I've given you at least some low-dimensional examples of computing Renyi entropies from these Lorentzian in path integrals. And it'll be really good to extend this further and test various calculations that have been done. But by setting them up, I think either it may be that in some of these JT gravity coupled to CFTs, one can actually just go through and redo the page curve calculations with our setup. Because there are two pieces of the calculation. One is a gravitational calculation, but the CFT calculation should be doable in real time in some suitable way. So with that, let me stop and see if there are further questions.
Okay, thank you very much, Mukund. So there's plenty of time for questions.
Hi there, Mukund. Can I jump in with a question?
Certainly.
If we go back to your example, you wrote a metric and it has an n in it. Am I supposed to think this metric makes sense for integer n, or is it really a metric that I can apply for any number n, any real n? And I'll say the follow-up is, well, you know, you showed what was important was crossing the light cones. Mm-hmm. And so I have a hard time imagining, you know, how many light cones am I crossing if n is not an integer? Like, right. What does that geometry look like?
Good. Yeah, I think I did intend n to be integer.
Okay.
And then there's a even number of light cones you cross. You're asking.
So would the philosophy be then that I'm evaluating this for arbitrary integer n, and then I'm analytically continuing an answer to.
I mean, in n, I
approaches
think I
one.
still have to do usual very analytic continuation, I think.
Yeah, okay.
Yeah. But I mean, I guess you're right in pointing out the sort of a certain tension in the philosophy, because we have multiple analytic continuations going on. I wanted to disallow myself from doing the analytic continuation in time. So that I sort of did, but you might complain rightly that the I epsilon is a prescription that sort of comes is born out of that. But one thing I can say is that the I epsilon can be employed even when our boundary sources and for the metric are not analytic.
Okay.
So that I think is fine. That just is a question. It's a question of maybe I'll say it this way. Physically, the way I thought about it was that if you have a source of energy on the splitting surface, if you had a shock wave running to the past, that would be strange. Because nothing happened in the past till you put in the geometry was what it was till you decided to compute the entropy. So you should see a physical shock going back in the past. And that requires definition, and that's where this I epsilon comes in.
Okay.
The second part about n analytic continuation is a good question. I think if we can try to avoid doing the replica and doing analytic continuation in integers, that would be great. I wonder if we can use some resolvent trick like what G and Eric Doker have been using to rethink this problem through in that context. I haven't thought that through, but
okay.
It's a good question.
Okay, thank you.
So when you said when you talked about the derivation of islands, like, do you just have in mind like reproducing the known story, or like you have a hope for getting some genuinely new insights from these sort of manipulations?
Okay, so certainly, I mean, sanity check would be reproducing the known results, which I don't think is a way. I mean, I think from the way the calculations have been working, I think that will work. The famous last word, because we haven't done the calculations, I don't know if it'll actually work, but I think my intuition says it should work with some effort. But what I would be after is something like this. If you look at the calculation of that entropy time step by time step, because at each time step you'll construct a new geometry. You'll be constructing you'll be doing a new calculation. And I'd like to see how in that calculation you see the transition of what happens. I mean, I can tell you lots of other interesting problems where I don't know the answer, which may be easier to tackle. So, famously, we know lots about instantons in quantum field theories, which we use to say something about vacuum structure and about the structure of the phases and so on. But all of those are Euclidean computations. How do you actually get the physical vacuum in Lorentz signature without using the Euclidean crutch? So any such thing that you can understand would, I think, help. And in the gravity context, what I would really like to see is sort of a systematic temporal evolution, which says, here's where. So what is clear is the following. If you go back and assume the island formula, like was done in the beginning by Pennington and Almeri, Don, Henry, and Netta, then you just compute with that prescription and you see the exchange of dominance of different geometric surfaces. And you know that leads to the correct answer, if you like. There's a post-facto justification from the path integral. But I'd like a sort of narrative which says, here is the history of the space-time, and here's how the geometry evolved, and this is what happened in that process. That may be ambitious, but if one can get there, that would be, I think, quite impressive.
Well, if there's no further questions, let's thank Mukund again.
Thanks, folks.